All right, let's take a second and look at two more laws that you may find of interest, or obviously I find of interest, or I wouldn't be talking about it. And they're one of them's a simple law, one of them's kind of it's a really easy law to solve for, but it's kind of a difficult concept for some people to wrap their mind around. But the first law that I want to talk about is Dalton's law of partial pressure, and Dalton's law of partial pressure is quite a simple law to remember. It simply states that the total pressure is equal to the sum of all of the partial pressures. Okay, so as we look at the atmosphere that's around us, 78% nitrogen, 21% oxygen, and roughly a percent of various other trace gases. All of these different gases are exhibiting a certain amount of pressure. If we look at them collectively, the total pressure is around our area, since we are very close to sea level, is around 1 atmosphere total. So our total atmospheric pressure would be 1 atmosphere, or if you wanted to say 101.325 kilopascals, or 760 millimeters of mercury, 760 torr, ever how you wanted to express that. That's the total pressure of all of these gases. Now, what if we're not interested in the total pressure, but we're interested in just one of those gases' pressures? And that typically is seen, or chemists typically see that when we are interested in collecting gas by water displacement. And this is an apparatus that I have here, and we're actually going to practice this in lab. And what we have here is we have a gas generating device. We have some acid, in this example it's sulfuric. Sulfuric's really nice about putting holes in clothes and skin, so a lot of times I like to use hydrochloric acid. But we've got some acid in this thistle tube, which you should remember from the first chapter, in an Erlenmeyer flask. So this one is a vacuum flask hooked up to a gas collecting device. Now, this is a pneumatic trough, or kind of a representation of a pneumatic trough, and this is a gas collecting bottle. We've used the gas collecting bottles before when we talked about, or not when we talked about, when we actually performed the lab collecting oxygen and carbon dioxide and setting the wooden splints on fire and putting them out. Hopefully you remember that. But in this example, we're capturing hydrogen. What happens is this reaction occurs and hydrogen gas is given off. And this hydrogen gas is wanting to escape, but it can't escape. It goes down this tube and starts to bubble out the end. Well, we put an inverted gas collection bottle that's full of water into it, and this gas bubbles up into this bottle and pushes the water out. And what you end up with is hydrogen, or mostly hydrogen molecules, with a few water molecules. So this is a mix of water vapor and hydrogen gas. But what we're interested in is the pressure of the hydrogen, because that's what we want to know, how much of that gas that we actually have. So we have a way to calculate that. Okay, the hydrogen gas is collected over water at 22.5 degrees Celsius. Find the pressure of the dry gas if the atmospheric pressure is 94.4 kilopascals. All right, we're looking for the pressure of the dry hydrogen. Okay, the total pressure is the atmospheric pressure that we have around, and the pressure of the water in kilopascals is 2.72. Well, where did we get this number from? Well, there's a table in your book that lists the vapor pressure of water at certain temperatures. Okay, and we look up the temperature, 22.5 degrees Celsius, because that's what it tells us that the temperature is, and we find that partial pressure, or that vapor pressure of water, and it's 2.72. And we would simply plug that into this equation. The total pressure is equal to the pressure of the hydrogen plus the pressure of the water molecules. Now, total pressure is the atmospheric pressure. Pressure of the hydrogen is the unknown. Then the vapor pressure of water from the table that we looked up is 2.27. We would simply rearrange this as a subtraction problem and get 94.4 kilopascals minus 2.72 kilopascals for a pressure of the hydrogen gas at 91.7 kilopascals. Remember, in this addition and subtraction, we're going to round to the least number or the least precise decimal places, which in this one is the tenths place right here. So let's look at a slightly different problem where it's very similar. Gas is collected over water at a temperature of 35 degrees Celsius when the barometric pressure is 742 torr. What is the partial pressure of the dry gas? Okay, so our total pressure is going to be 742. A certain gas, so any gas, it doesn't specify which gas, is collected over water at a temperature of 35 degrees Celsius. So we have to go to the table in our textbook and look up the vapor pressure of water at 35 degrees Celsius. And since we're working with torr, we have to get that water pressure in torr. Okay? So we look this number up, 42.2 torr, and we're trying to find the partial pressure of some gas. So we simply plug this into our Dalton's Law of partial pressures. The total pressure is equal to the pressure of some gas plus the vapor pressure of water. Total pressure in the atmosphere is 742. The partial pressure of that should say gas. The partial pressure of some gas plus 42.4 torr, which is the vapor pressure of water. So the partial pressure of this gas is 699.8 torr. So that's the pressure that this gas has. We can now take and solve problems since we know this pressure. For example, volume. We know the temperature. We can get the volume of this gas. How much volume of this gas do we have? Now, the very last gas law of this chapter, very last thing we're going to talk about is Graham's law. And Graham's law talks about the rates of diffusion and effusion. Diffusion is the spreading of gas molecules throughout a container that is evenly distributed. Remember, like the spreading of perfume scent. Effusion is the passing of gas molecules through a tiny opening in a container. Remember, like I said, a hydrogen balloon, the helium balloon. The helium will eventually diffuse out of the hydrogen. Now, we're interested in studying how fast can these molecules spread out. How fast can these perfume molecules be carried throughout the room? Or how fast can that helium diffuse out of that balloon that we're interested in? Well, when looking at the speed or the velocity, we must take into consideration a couple of different things. Okay, we know that kinetic energy is determined by the temperature of the gas. The higher the temperature, the more energy, the faster things move. Okay, think about going outside. Are you going to be more apt to go outside in the summertime when it's warm or the wintertime when it's cold? Most of us are going to like to go out in the summertime when it's warm. I mean, a few of us do like to hunt, but for the most part, we like to go out in the summertime when it's warm. At the same temperature and kinetic energy, heavier molecules move more slowly. And just think about this. The more cumbersome, the bigger molecules like sulfur hexafluoride, you got sulfur in the middle and 6 sulfurs hanging off of it. That's going to move a lot more slowly than a small helium atom at a mass of 4, which sulfur hexafluoride is, right off the top of my head, I calculated it last week, 130 or 230 something grams per mole. So it's a much larger molecule. So the larger the molecule, the smaller its speed. The larger the mass, the smaller the velocity. And this is an equation that we will use when we get to thermochemistry. It says kinetic energy is equal to 1/2 the mass times the velocity squared. Now, this is Graham's law. Graham's law is the rate of diffusion of a gas is inversely related to the square root of its molar mass. Okay, so the speed of gas A over gas B is equal to the square root of the mass of gas B over the mass of gas A. Now, we will not be solving for an actual velocity. Rather, we will be solving for a ratio here. Okay, this gas moves this many times more quickly. It's a ratio, a 1 to whatever ratio of velocity. Okay, so determine the relative rate of diffusion for krypton and bromine. The first gas we're going to say is gas A, and the second gas is gas B, and we're going to plug it into Graham's law. Okay, so we take the mass of bromine. Remember, bromine's a diatomic gas. Its mass in the monatomic form is 79.4 something. over the molar mass of krypton, which it's a monatomic gas, 83.80. Solve this problem, take the square root of the molar mass of bromine divided by the molar mass of krypton, and we're going to get a proportion of 1.381. This proportion tells us that krypton diffuses 1.381 times faster than bromine. That means it's moving around 1.31 times faster than bromine will. Okay? That's very simple way to solve that problem. Now, let's look at another problem. A molecule of oxygen gas has an average speed of 12.3 meters per second. Meters per second are the meters per second is the units for velocity at a given temperature and pressure. What is the average speed of hydrogen molecules at the same conditions? Okay, so we're looking at hydrogen and oxygen here. We'll call oxygen gas B and hydrogen gas A. So we'll put the unknown gas as gas A. Alright? So we're taking the velocity of the hydrogen over the velocity of oxygen and comparing that to the molar mass. And this is simply a math derivation at this point. We put in our molar masses. Since both of these molecules are diatomic, we must remember to multiply their molar mass times 2. Okay, take the square root of that, and you end up with the velocity of hydrogen over 12.3 meters per second equals 3.980. Then we take, and we have to get 12.3 out from under the velocity of hydrogen. We multiply both sides by 12.3, and we end up, the velocity of a hydrogen molecule at this temperature is 49.0 meters per second. That means that the hydrogen will diffuse across a room at a rate of 49.0 meters per second. That is that's really fast. That's a second. That's 40. It's moving 49 meters a second. That's the distance, half the distance of a football field every second. So that's quite quick that hydrogen diffuses across the room. All right, let's look at another type of problem. An unknown gas diffuses 4 times faster than oxygen. Find its molar mass. Okay, so we end up, it's 4 times faster than that of hydrogen. So the mass of gas A, which is going to be our unknown, is equal to 4.0. That's the ratio that it moves. Remember, we talked about this as a ratio if we're solving it without knowing specific velocities. Okay, now we're going to solve this. We have to get rid of the square root sign because our unknown is in the square root. How we would do that by squaring both sides. So we get 16 is equal to 32.00 grams per mole, which is the molar mass of oxygen. Remember, oxygen is a diatomic gas, over the mass of gas A. Okay, now we need to get gas A by itself. And we do that by multiplying both sides by mass A. Then we're going to divide the 16 and make it go to the other side. So the mass of the gas is 2.0 grams per mole. That would tell me that this gas is probably going to be hydrogen. And that wraps up those last two laws.